Welcome to my Artificial Intelligence through Artificial Intelligence YouTube channel and the Introduction to Deep Learning and PyTorch course. So far, we have explored activation functions in depth, covering their categorizations and the different types of nonlinear functions used in neural network. However, while watching videos on activation functions, we noticed that some key terminologies were often mentioned but not thoroughly explained. This and upcoming videos focus on clarifying these key concepts, including saturation, vanishing gradient problem, and zero-centered output. So, let's dive in, starting from saturation. Saturation is a common issue in sigmoidal functions, including tanh, sigmoid, and softmax. So let's explain the concept of saturation with respect to tanh and sigmoid functions. A neural network classifier consists of input nodes, hidden processing nodes, and output nodes. If the sigmoid activation function is applied to the output layer, the output node will have a value between 0 and 1. When using the tanh activation function, the hidden nodes typically have values ranging from -1 to +1. A saturated neural network is one where most of the hidden nodes have values close to -1 or +1, and the output nodes have values close to 0 or 1, causing training to stop or progress very slowly. So far, we have developed a clear understanding of saturation. Formally, it can be defined as saturation occurs when a neuron's output approaches the extreme limits of its activation function's range, also called as asymptotic limit. In this state, even significant changes to the input produce negligible changes in the output, effectively making the neuron unresponsive to new information. Here is the graphical view of tanh and sigmoid functions with saturated regions. The graph of tanh function is showing that output of the tanh function in the saturated regions is close to +1 or -1, making the gradient nearly 0 and leading to the vanishing gradient problem during training. The graph of sigmoid function is showing that output of the sigmoid function in the saturated regions is close to 0 or 1. Saturation occurs when output of the sigmoid function is greater than 0.8 or output of sigmoid is less than 0.2. In these regions, the gradient becomes very small, leading to slow learning or vanishing gradient. Saturation is a major challenge in neural network training as it causes the vanishing gradient problem, reducing the model's ability to capture information and learn complex patterns from data. Furthermore, saturated models are prone to overfitting, which means the models perform well on training data and not on new, unseen data. Illustrating causes of saturation, the sigmoidal functions such as sigmoid, softmax, and tanh are highly susceptible to saturation, particularly when the neuron receives very large or very small input values. Additionally, extreme input values can drive neurons into saturation, regardless of the activation function used. As you know, saturation is a major issue that slows down learning in neural networks and prevents them from capturing complex patterns in the data. To mitigate saturation, we can take these steps. Using less saturation-prone activation functions, such as rectified linear unit or its variants, like leaky ReLU, can help mitigate the problem. Tuning the learning rate appropriately can help prevent the network from becoming trapped in saturated regions. Initializing weights and biases properly can help prevent neurons from entering saturation. Batch normalization can also reduce the likelihood of saturation. That wraps up today's video. I hope you now have a good understanding of the concept of saturation, its causes and solutions. If you found this helpful, don't forget to subscribe, like, share, comment to stay updated with this series.